video clips which were supposed to guide you on some areas of study on PDI, but I want us to look at the test of okay. Sometimes you have test signals we use for test signals for stability. We have the impulse, we have the step, we have the sinusoidal, and the ramp. Okay, when we are testing, some people are still joining us. When we are testing on stability, you're expected to, we have a transfer function of some values over some values. And so the output with respect to the reference will give you some values here. And now if you want to test, you have to feed maybe uh, user step input. And a step input can be a signal, maybe a rectangular signal, maybe here is 10 volts or 1 volt, something of that kind. Or you can use an impulse signal, which is just a zero and just attaining some level there. So normally, when the signal is, when you look at the poles and the zeros, you find that in you have two types of signal whereby you can have second order signal and first order signals. So look at the second order most likely, but we find that in a second order signal, so you can find that is a step response, whereby the transient unit is responding to the first, very fast, the, the first few seconds, it moves rapidly, the transient state, and then it switches, whereby it starts moving in a slope up to the maximum level of the step input. So the 90% of the signal is on a transient state, and the others is on a steady state response. So the standard test signals are the step signal, input no, the impulse signal, the step signal, the ramp, and also the ramp is this one here. I think this one you've done in the other uh, training that you had with the other teacher was teaching you control system one. Now, response of the second order signal, if you have reduced your control system to canonical form, if you reduce the signal to the canonical form, you can just admit somebody here. And the canonical form is that you had very many blocks with many feedbacks, maybe. And therefore you reduced it to canonical form that you'll have only one block, which is having the input and output with the feedback, maybe. So this is the canonical form of the transfer function with one block. You have reduced the block to one block, and therefore you have that one block. If this one block here is giving you this kind of expression, then there's a second order system. If it is a mechanical system and you have converted it to resistor, inductor, and capacitor, the areas whereby we have both so in areas whereby we have both the capacitor, the inductor, and the resistor, maybe in any order, if you have just done the, the translation, you'll have a second order. You have a second order system when both of these three exist. But if only one or two with the resistor exists, then you have a first order. So second order have s raised to power 2, and that one I think you've done. Now, in a second order response, and if you have done your computation right with a closed loop transfer function, this is the canonical form we expected of you. Then you put this block is the GS, Then this one is the feedback. So you bring the block, which is years here, then add this part, then you get this expression here. This expression is a second order, whereby you have the Wn, which is the natural frequency of the system. Wn is the natural frequency of the system, and the damping factor is what is given here. Just look like a D. Now, the power S is 2 in the denominator term, hence the above transfer function is the second order, and the system is said to be a second order system. Now, this lower part is known as the characteristic equation, and you can put it to 0. You want to see the poles and the zeros here, the poles of that cell, poles, because any numerator here, when you put to 0, you want to factorize it and get maybe the response. You find that S is going to be equal to negative this value plus natural frequency into the square root of this z term, and that's 1 squared. So the two roots are imaginary when the damping factor is equal to 0. When damping factor is equal to 0, then this is going to be negative. The square root of negative 1 is going to give you some imaginary function with a j or I. The two roots are real when this del is equal to 1, this z is equal to 1. So all of this is going to be 0. So you have this other 2. Or when this is equal to 0 with all these parts well, this will be done in quadratic equations. And it's allowed that the two roots are real and not but not equal when del is greater than 1. The two roots are complex conjugate when it is between 1 and 0. If somebody is having a dt, can you mute your phone? Somebody has not muted the phone. So the step response for the second order uses the Laplace. The R of S, the reference, is always 1 over S. That's only covered in control 1. And therefore, we know that the transfer function of second order in a closed loop system is given by that. So when z is equal to 0, then you substitute this z is equal to 0 in the transfer function, then this part is going to be 0. So the remain with this kind of thing. So Cs is equal to this function multiplied by Rs, cross multiply. Then you'll get that the equation will look like this. And applying the Laplace inverse transform, you'll get C of t is equal to 1 minus cos Wnt multiplied by ut. So the unit step response of the second order system, when the zeta or delta is equal to 0, will be a continuous time signal with constant amplitude and frequency. You can easily do this using your calculator. You go to calculator and go to FX. Go to FX. So you know our equation, as far as this thing is concerned, just a minute, and do something. Okay. Okay, we have said that in a step function of second order, the equation is going to look like this. C of t, S is equal to 1 minus cosine over Wn of t into u in the step response. So if you go to your calculator, go to the FX, then you'll write 1 minus cos of x. We take all of this as x, because this cos of x times maybe 10 times 10, a unit response, maybe 10. So you'll have a table of values, maybe 4 of them, 1, 2, 3, 4, or 5. Then, so we have x and f of x. So supposing I have I start from maybe x is equal to 30. Bigger problem. X is equal to 30 up to 180. So I convert it to in a spacing of 30 also. So I'll change it to radians. So 30 is going to be, I'll have 0, 0.5, 1.6, 2.1, 2.6, and maybe 3.2. So my functions will be minus 0 is just going to be minus 9, minus 8.9, minus 8.9, minus 8.9, minus 8.9, minus 8.9. So it is going to be, according to this, when you if you draw a curve, maybe 0, no, 0.5, 1.6, 2.1, maybe I'm just writing for the sake of 2.6. But it's always good to have a scale. Then you find that all of these values, though they're negative, because my 1 minus something, this one is going to be bigger, big, that's why it is giving us negative, because it's bigger than this. So we shall have minus maybe 10. Then you find minus 9 is here, minus 8 point something here. So it's going to give you almost a constant signal for what we're trying to say. So that one is going to give us that. He's saying the unit step response, second order system, when that is zero, will be a continuous signal with a constant frequency. And in the case when delta is 1, we shall, 1 will be here. This one, so the look of this middle section will be 2 omega ns, the natural frequency multiplied by 2. And when there's a step response, you'll get this. And by partial fractions, you'll be able to come down until you write the inverse Laplace transform in this order. So you can go back to the tables. I'm also writing where I am right now, so I'm just trying to show you the way. So I'm not writing the equation, so can I write it on my book? It is 1 minus E minus omega nt minus omega nt E minus omega nt bracket ut. Good. So what I'm trying to say is this. My expression is that C of t, which is the inverse Laplace transform, is 1 minus E omega nt minus omega n E minus omega nt into U, a step function. So in my f of x calculator, I'll go to 7, then I write 1 minus E. All of these things are going to be my x. This one is my x minus x into minus xt, x itself, not xt. Then I multiply by 10. So when I enter these values, I will get these values here. So when I plot x between 1 to 5, 1 to 5, with an interval of 1, I'll have x 0, 1, 2, 3, 4, 5, then f of x would be 0, 2.5, 5.9, 8.0, 9.0, 9.5. And if I draw this kind of thing, I'll have my 0 there, I'll have my 5 and 10 because I've multiplied by 10, so it's a step response of 10. So this is 1.5, this is 2.5. Then I have my 1 here, my 2, my 3, my 4, my 5. So 1 is supposed to be, 0 is supposed to be 0, 1 is 2.5, 2 is 5.9, 6 somewhere there, 2 is 5.9 somewhere there, 3 is 8, 4 is 9.0, 5 is 9.5. So I'll move the signal will be, the response is rising exponential form. So it will not just come to 10 directly, but it has a slow response. But this slow response, you can know the rate of the time of the rising time, depending on the rate, because some of the signals under some kind of compensation, they will move faster. Some will move more faster to meet the target there, or some will be moving so slowly up to that level. But then, according to the equation, our step will be following this route here. But as you learn more of these topics, we shall be able to see the rate of response based on the rise time and what is causing it. So in any way, I know all of you, we are going to do this work at your own pace. So you just go to the calculator, then you go to the, if you want to just put fx, then 1, in bracket put 1, then all of these put as x because they're almost similar. Even this one is similar, put x. So how do you put x? You go to alpha. You go to, there's a shift and alpha. So alpha is having another color there. I don't know, there's a purple. So you'll just E minus x into E minus x. This t there, you don't mind about it because our x is what is varying, a lot of this, WNT. And you multiply this by 10 and c. Even if you put 5 here, it will be moving towards 5. So the unit step response of the second order system will try to reach the step in a steady state. So it's moving in a steady state. So when the del is between damping factor between 0 to 1, but not exactly 1 or exactly 0, we'll be able to write the equation in this manner. And the final analysis will come down up to this level. And you may end up now writing this equation. This is a constant. This is a constant. So you just say it is something that you don't need because you just 1 minus sine x plus maybe 30 degrees into 10. So you'll find that in this kind of arrangement, when you plot, when you plot, you'll find that it is a damping oscillation. It can be a damping oscillation. It is vibrating, then moving slowly to some kind of like that. So, but if you have two values, it could be imaginary. It can be like that, so that the damping will be both with negative and positive sense. And it's like that. So when del is between 1 and 0, normally it is oscillation with a damping towards as time increases. Um, but in any case, if this del is greater than 1, and substitute one of s, you'll get some kind of this equation, this minus this. And since it is overdamped, the unit step response of second order system when delta is greater than 0 will never reach a step function input in a steady state. So in this case, it's going to be overdamped. It is going to be overdamped and will never reach. When it is greater than that, it will never reach. If there's an step function there, it will be overdamped. It will just move like this. Overdamped. And will never reach here. You just go continue moving in like that. And that is that. So this one you have done with the in system one, we have a delay time. We have which is given by TD, and rise time. Rise time you can get it T2. TD is the delay time. Why do that T2 there or TR? Rise time. The rise time is TR. This is written as T2 here. Okay, TR is T2 minus that. Okay, I get it now. So rise time is T2 minus T1. So T2 is supposed to be this expression. T1 is T1 here, of the given you. The theta. Okay, I'm looking at it. There's a T2 here. So it is the time required for the response to rise from 0% to 100% of its final value. This is amplitude of the underdamped system. For the overdamped system, consider the duration of 10 to 90, the final value. So 10% is T1, 9% is T2. And the all of that is TR. Now the peak time is also given by TP, which is pi over omega d, the damped frequency. Then overshoot is MP in that. So overshoot is give me MP there. A time for that is given to that. Then settling time is this expression we have done it before, and so on and so forth. Now let me just look at something again here. Okay, I want us to come here a little bit, and this is a summary. The damping ratio, we say that when it is equal to 0, pure imaginary and undamped. It's pure imaginary and undamped. So it's going to be negative value, and maybe you said it is constant. When it is between 0 and 1, it's complex conjugate, but it's underdamped. When it is greater than 1, or equal to 1, it is repeated roots and critically damped. And when it is greater than 1, it's two distinct real poles overdamped. So if this is the Wn, positive and negative, imaginary, so you can see that when it is here, when it is equal to 1, repeated real poles, critically damped. And the distance between all this is WD, this Wn, which is natural frequency, and that damping value is cos of theta. So if this is the WD and this damping terms of N, this distance, then the phi there, the angle there, because of theta is that value. So this is some of the things I was talking about that can be okay. If you draw a rectangle triangle, this is the sine side, the cosine side, and you can be able to use this formula to know. So the cosine of this cosine of theta, this is the angle theta, is this value, and the sine of this theta is 1 minus that. So you find that when theta is equal to 0, you can see the signal is with the same amplitude, up and down, equal to changing like that. When it is 0.1, and 0.2, 0.5, 0.7, it is just still oscillating, but now the damping, the damping has been lowered at 0.7 when it is almost supposed to approach 1. So 0.99 something, 0. Maybe 8 something, it will be 0.7 is the best normally chosen for the damping pressures. 0.7. This is almost the appropriate one for every form of damping. But when it is now 1 or 2, it is critical damped. No damping means that we are controlling the oscillation. So normally allow a tolerance for that damping can be given 0.2%. So delay time is the time required for response to reach 50. And that time is 0 to the time required for rise from 0 to 100 standard value. And peak time is the time we require the response to reach the peak of the time response of the peak overshoot. Settling time is between 2% to 5% tolerance. To think of that. And steady state error indicates that the error between the actual output and the desired output t tends to infinity. Now, I gave you some work to do. Then I gave you some kind of you can try to drive the solution of this expression mx squared plus kx equals 0 and plot the result for at least 2 periods with omega n is equal to 2 radians per second from x0 is equal to 1 millimeter and v out is equal to 5 millimeter per second, the velocity. Ali Mohammed, you come later, I don't know why. So if you're supposed to get a solution for that, assume that this expression now is equal to 0. Assume x of t is equal to AER of t, then x is equal to that expression there. And when you substitute them like that, you get 0. So you get R with this. I'm just giving what is given here. And x is going to be something like that, and x2 is going to be something like that. Then Wn is going to be that, 2 radians per second. The sum of x2 and x is also the solution, so that the total solution is given by that. Then substitute, you get equation, and after getting everything, you find that the answer is going to be something like this, and it will be something that is oscillating, not stopping. So it is not a stable system, but continuous oscillation. So I'll send you some of these this is solution to the problem that you can read, and but it depends on whether you've gotten the answers to the problem I gave you. What I want you to do now is just to go back to um, the first things that we did first. I want you to try the step response and use tables, mathematical tables. Use mathematical tables on second order system. Step response, uh, uh, let's say impulse and RAM. So I want you to draw for second order. I want you to put use tables to get values depending on what we're going to choose, and draw the graphs and send them to me before next week. You see my email. Or use the black, classroom. But if you use my email, I'll be able to mark and send to you immediately. And these marks are going to be put in the system in your semester assignment. Okay, I think last time I gave you some work to do, some video clips to read. I want you to just do on this one to see the response of some of the things you're doing there on the card I gave you for the classwork. You reach a point whereby you'll be analyzing this step response just to check the behavior of your transfer function when you feed either step response, standard time test, impulse, or RAM. But just use the step response in most cases, and impulse if possible. And RAM is just for the sake of understanding the concept of well. This is for your life, and this is a time for you to read this area. Unless there's a question, I think I'll stop there. Any question, please?
Yes, excuse me, sir.
Go ahead.
Regarding that assignment,
Yeah.
for second order,
Mm.
the damping ratio could be 1, could be less or greater than 1 or 0. Do we draw the graphs for all the 4 cases or just one case?
Oh, that's a good question. Okay. What I want you to do is that you check when, like the one I've just given to you, Uh, a step response. Okay, I wanted it to look like a step response. Uh, there's one here which is giving us when this one is giving us reading. So the best thing is to draw it when it is equal to one. I want you to draw check whether it is when the number is equal to one. So for that case, because it will not be easier to reach. I just want to check the response and it's equal to one. It's a good question. Because I know between 0 to 1 it's going to take you long to get the equation right. But I don't want to go that level. But just for the sake of understanding and see how you can draw graphs, I don't want to take you to greater than 1 to either between 1 and 0, but let's let it be equal to 1. Very good question. Thank you. George Mwangi,
Yes.
any other question, please? So, have a good time, please. God bless you.